like I said, I really hope your biology went well yesterday and your English went well today. And in this live, we're going to go through some exam tips on how to approach the exam.
Biology went well yesterday and your English went well today.
Sorry, I was just, I'm also live streaming on YouTube, I think, although it's the first time I've done that. The reason I'm doing it on YouTube as well is because I'm going to share my screen so that you can see me drawing things like dot and cross diagrams and stuff. So if you'd rather see the full screen and you've got your laptop in front of you, then please do join me live on YouTube as well. But I'll be explaining everything on both Instagram and YouTube. So welcome to those of you guys who've joined so far. We'll just get started now as soon as possible. So as I said, the screen share is on the YouTube live. YouTubers, I'm sorry if you can see my camera and I'm not looking at you. I'm going to be looking at the camera for the Instagram, and I'm going to be doing the screen share on the computer on YouTube. So starting off with some exam tips, how to approach the exam. And some of you guys are really stressed about revision, and it's really, really important to cram as much revision as possible, as learn as much as possible. But how you approach the exam can make just as much difference to how many marks you get. So the first thing is read the whole question. Okay, if you don't read the whole question, you could miss out some really, really useful information. And as that goes on to the second point, which is use all the information. So I'll go through some examples in a second when we look at a past paper, but there are often really useful pieces of information in the question that people skip out because they just skip straight to the question and they don't use all the information that's been given to them. So make sure you use all the information in the question. The third one is answer every single part of the question. So sometimes the question will be broken down saying like things like describe and explain, or in a calculation question, it'll say use 3 significant figures, and you actually get a separate mark for calculating it to 3 significant figures, as well as getting the answer right. Another thing relating to calculations is make sure you always show all of your working. It's great if you get the answer right and you get full marks, but you might not get the answer right because you've made a mistake along the way, or you've made a calculator error. And if you show your working, then you could get lots of credit even if you don't get the right answer. So make sure you show your working as you go. The next thing is be really specific. So I already put this on my story yesterday, but examiners from AQA board said that there was a lot of students last year who wrote it and they, and that doesn't show the examiner that you know what you're talking about. So if you know what you're talking about, then don't use the word it, say the metal or the solution. Be really specific about what you're talking about. Don't use the word amount, because the word amount, again, is really vague. This often comes up in practical questions. What are you going to keep the same? Don't say the amount of substance, say the volume of solution or the mass of the solid. So be really, really specific, as specific as you can. Point 5, tip number 5 is check your answers. This might sound like a waste of time, but if you check your answers, you can check if you've got a calculator error. Sometimes you don't have to go through the whole question again, but you just have to think in your mind about if that number makes sense. Check especially calculations and equations. Finally, keep an eye on the time. Okay, so if you're watching on YouTube, you'll be able to see I've just put up the front page of the exam, which often people ignore. You get an hour and 45 minutes if you're on triple, or an hour and 15 minutes if you are on double, and you get 5 marks more. You get 5 minutes more than that number of marks. So basically, it's 1 mark per minute. So 100 marks and 1 hour and 45 minutes. That's basically 105 minutes for 100 marks. So try to keep an eye on the time, especially on the longer answer questions. So like the 6-mark questions. Obviously, you might want to spend a little bit longer on the 6-mark questions. You might want to spend 10 minutes, but that means that you can only spend half a minute on some of the shorter questions, okay? So just keep an eye on the time and make sure you're leaving enough time for the rest of the exam. When do you get thinking time? I would say try to make sure that you're going through the first part of the exam, which is the easier part of the exam, as quickly as possible. And then maybe about halfway through, try to make sure that any of the questions that you're going through, particularly the longer answer questions, you're making sure you leave enough time for the rest of the questions later on. So remember that exams always start with the easiest, most simple questions first, and they get towards the harder questions and longer questions near the end. So the last thing you want to do is leave yourself not enough time to finish the exam. Okay, so try and go through the questions at the beginning quite quickly. They're intended to be a little bit easier, to be a bit of a warm-up and stuff. Do you think it's better to start from the back to the front? That's a great question, and it depends on how you like approaching things, but the exam is written how it is for a reason, and it is normally easier and better for your mind to start at the beginning and move to the end, because your mind does warm up with the easier questions. Having said that, try not to spend too much time at the beginning, okay? It got all broken, I didn't hear anything. Okay, I'm not sure what that bit was, but it was just, I was answering the question, do you think it's better to start from the back to the front? I don't suggest starting the back to the front, but I do suggest trying to leave enough time for the questions at the end. Okay, so just going through some more tips and stuff now. If you're on the YouTube live, you'll be able to see now that I've got the topics for all of the different exam boards, and you can see that there's a lot of overlap between the exam boards, but I know some of you are on AQA, some of you are on OCR, some of you are on Edexcel, and I want to make sure I go through as much as possible to make sure it's relevant for you guys. But there are a few differences. Mainly the difference between Edexcel and the others is that Edexcel has equilibria in it, which the other ones don't. But otherwise, more or less, it's the same. It says it's still breaking up. Okay. That's annoying. Again, I'm not sure. Maybe it's because I'm on my Wi-Fi. My Wi-Fi doesn't always work as well as my intranet cable. So if you are having trouble on Instagram, then have a go at trying YouTube and seeing if that's better, because my streaming will be better on my end. If it's yours, then I'm not sure. There's nothing else that I can do for you guys. But okay, so we're going to go into some actual revision stuff now. This is where it's going to be much more important to be looking at the live stream on YouTube if you want to be looking at the details of what we're going through, and also making notes as we go along. Okay, so bonding. I haven't gone through that much on bonding in the last few lives, so I'm going to start with bonding. Ionic bonding is obviously oppositely charged ions, positive and negatively charged ions, attracted to each other by an electrostatic attraction. The key thing with ionic bonding is that we have a metal and a non-metal. Okay, so sometimes you'll be asked what type of bonding is present in a compound. Sometimes you'll be asked to draw an ionic compound, and it's really important to know that that's a metal and a non-metal bonding together. The metals always make positive ions, and the non-metals always make negative ions. And the charge of the ion, the YouTube channel is called Boost Chemistry Revision, and it's a link on my bio in Instagram. So if you go to the link in bio, you should see the link for my YouTube right at the top there, okay? Okay, someone says, oh my God, it's not working. Could you restart the live, please? Can you guys, if you're on, can you let me know if it is working, or if it isn't working, what the problem is? If it's my Wi-Fi, I can go and restart that and come back in a couple of minutes. But obviously it might be working for some people. So I'm not really sure whether to keep going here or not. Could you let me know, guys, what the problem is on Instagram? And if you are having problems with Instagram, then feel free to switch over to YouTube, because I'm going to be covering the exact same thing, okay? So just a sec. Yeah. Okay, so you should also be able to see my video on YouTube now as well, but I haven't done it before, so it's all a bit new. Okay, so back to bonding. Some people are saying it's working fine, so if it's not working for you, it's probably your Wi-Fi. There's probably loads of people online at the moment watching videos and revising and watching videos of other people. I know Science with Hazel's on tonight, I know Primrose Kitten's on tonight, I know Head Tuition's on tonight. I think there's lots of tutors on tonight, so I'll keep going, and hopefully it will work for some of you, and if not, then go to my YouTube, see the link in bio. Okay, so we've done ionic bonding. So covalent bonding. Covalent bonding is between two non-metal atoms, okay? And the key thing is that it's a shared pair of electrons, okay? In the exam, if you're asked what a covalent bond is, you get the mark for saying a pair of electrons, okay? It's a shared pair of electrons. Now, the slightly confusing thing with covalent bonding is you can have simple covalent bonding, which is where you have small molecules joined together by covalent bonds. And then in between the molecules is weak intermolecular forces. And it's the weak intermolecular forces that affect the boiling points of substances. So in the exam, they often ask about trends in boiling points of covalent substances. And that's all to do with the strength of the intermolecular forces. The larger the molecule, the stronger the intermolecular forces, and therefore the more energy it's going to take to break them apart. And those are key things to write down. So the longer or bigger the molecule, the stronger the intermolecular forces. Okay, don't use the word bonds for intermolecular forces. Okay, and if it's stronger forces, then it's going to take more energy to break apart the bonds. Okay, the other thing about covalent, you've got the simple covalent, which is the small molecules, and then you also have the giant covalent, which are the really, really large structures. The main examples you need to know about are diamond and graphite. Diamond doesn't conduct electricity, is really hard because all of the atoms are joined together by strong covalent bonds, whereas graphite does conduct electricity and is soft because it's made up of layers. And in those layers, the atoms are joined together by strong covalent bonds. And as you'll see on the YouTube, I'm drawing the structure of graphite, and you can see that you've got 2 layers of graphite, and you've got weak intermolecular forces in between because of delocalized electrons. Okay, so whenever you're talking about properties and bonding, with conducting electricity, being able to conduct electricity is all about whether or not electrons or ions can move. So graphite conduct electricity because it has delocalized electrons that can go through the structure, flow through the structure, and metals can conduct electricity because they also have delocalized electrons that can flow through the structure. Okay, so you may be expected for all of these types of bondings to draw the structure and perhaps even label the diagram. So here you'd write positive ion, and here you'd write negative ion. But it's most important for metallic bonding, where you have the positive metal ions, and you have the delocalized electrons in between. That's these negative things in between. So giant structures are ionic, covalent, and metallic. The only one that can be simple is covalent. Okay, and that's where you've got the difference between bonding, which is ionic, covalent, metallic, and structure, which is simple and giant. But both bonding and structure can affect the properties of substances. Someone said something about predictions, and I think that there's definitely going to be a question on properties and bonding. There almost always is in some way, but being able to link structure and bonding with properties such as melting and boiling point and conducting electricity is a really, really important thing to be able to do. And I reckon that's probably going to come up. So that's one of my predictions for this year. The layers aren't held together by covalent bonds. Yeah, this is talking about graphite. The layers are held together by intermolecular forces due to the fact that we've got delocalized electrons. This is for graphite. Just having a look at some other questions that we might have had. Is this for a specific board or in general? As I said earlier, and I'll just flick back to this for those of you who might be on YouTube, all 3 of the boards cover more or less the same stuff: atomic structure, bonding, calculations, chemical changes, and reactions. That includes displacement reactions, which is to do with extracting metals. And then Edexcel has equilibria, AQA has energy, and OCR basically is a mixture of those. So okay, now we're going to go on to dot and cross diagrams, okay, because this is something that's really commonly done not that well. Okay, so with one of the things to first think about if you're asked to draw a dot and cross diagram is that thing ionic or covalent? Okay, and as I said, it's to do with whether you have a metal and non-metal, or whether you have 2 non-metals. Okay, and that is how you'll decide. The ionic dot and cross diagram is supposed to look like this, okay, which is, as I said, you'll see on YouTube. You've got the metal has lost all of its outer shell electrons, and it's in square brackets with a positive charge, and it's either +1 for group 1 or 2 for group 2, group 3 for group 3. The non-metal has gained an electron or 2 or 3 from the metal, and so the the negative ion will have all of its own electrons, okay, so that in chlorine, that's these 7 here, plus the electron that is gained from the metal, okay, so it's going to have a full outer shell of electrons, and it's going to have a negative charge. And just keep in mind, so for example, if it's something like oxygen, it will have 6 of its own electrons, and it will need to gain 2, okay, and it's going to have a 2- charge. So remember, groups 5, 6, and 7 have charges of -3, -2, and -1, and I said already that groups 1, 2, and 3 have charges of +1, +2, and +3. So it's really important before you draw a dot and cross diagram to make sure that you know, is it ionic or is it covalent? Because the ionic ones need the square brackets with the charge and showing the transfer of electrons, so the metals lose electrons and the non-metals gain them. And the covalent ones are like this one down here, where you have overlapping orbitals. So the 2 orbitals overlap, and you have at least one shared pair of electrons. So this would be a single bond between chlorine atoms, but you can also have double bonds like between oxygen atoms, and that would mean 2 electrons being overlapped in that overlapping area. Okay, just make sure as well with covalent bonding, you do get a mark for the number of electrons in the overlap. That's obviously really, really important. But don't forget to draw all of the other electrons that are on the edge of that electron. So each oxygen has 6 electrons originally. So you have to have 6 crosses on the left-hand side oxygen and 6 dots on the right-hand side oxygen. And then all together, once they've shared the 2 electrons, they'll have 8 and 8. So make sure you count the correct number of electrons for each element in your covalent structure, and make sure you have the right number of overlapping electrons. It's really, really common that people forget to draw the extra electrons around the outside. So if that comes up, then make sure you count how many electrons are in each of those atoms and draw them all on, okay? Okay, so the next bit we're going to do is about acids, okay? So chemical changes topic is often to do with reactions of metals and reactions of acids, and they often come hand in hand. Acids react in 3 main ways. Acid plus metal makes salt and hydrogen. So a gas is produced, and that gas you can test for the presence of hydrogen because you've got that squeaky pop test. Now that may not come up in paper 1 because it's officially a paper 2 topic, because tests for gases, but it's useful to know, okay? And that may be something that helps you to distinguish what's reacting in a substance. So for example, if this was hydrochloric acid reacting with magnesium, then you have to be able to predict the name or formula of the salt that's produced, which is the metal and the non-hydrogen part of the acid, so chlorine in this case, and make sure that whenever you're writing a formula from scratch that you use the right charge on each of the ions. So magnesium is in group 2, and so it makes a 2+ charge. Chlorine is in group 1, so it makes a 1- charge, so we need 2 chlorines for every magnesium. That's why the formula is MgCl2, okay? And then hydrogen, again, hydrogen is one of those elements that exists in a diatomic molecule, meaning that it's got 2 atoms in the molecule. So hydrogen is always H2. So if you're asked to draw that equation or write that equation, make sure you remember that hydrogen, like oxygen, nitrogen, fluorine, iodine, bromine, and chlorine, is H2. So there's 2 atoms in each molecule. And that means we have to balance it by doing that. Okay, so balancing equations is obviously a really key skill that you'd be expected to know. It comes up in pretty much every chemistry exam, so make sure that you practice doing that. But if it's really, really, really hard, then just take a guess, okay? Some of you may have seen before my video on my trick to balancing equations, which is to do with drawing a table where you do, like, you'd say, you list out each of the elements like hydrogen, chlorine, and magnesium, and you just look at how many you have on the left-hand side and the right-hand side, and you do a tally, okay? And then that helps you to calculate how many you have on the left-hand side and the right-hand side. Okay, so feel free to ask questions as you go along. Cool. So Acid plus metal makes salt and hydrogen. Acid plus metal oxide makes salt and water. And this links to one of the required practicals, which is making a soluble salt. Okay, so for that, you need to know that you're going to add an excess of your metal oxide to the acid. That's make sure that the acid completely reacts. Then you filter the excess solid away so that you have just the solution, which is your salt solution, which would be your soluble salt solution. And then you need to do something to remove the water. So you normally start by heating it up to start to evaporate the water. Try and make sure you use as many keywords as you can in your answers. And then you don't keep heating it completely. If you want to have the salt left behind, you just start by heating it to evaporate some of the water, and then you leave it to dry. So it might take several days if you're just doing crystallization, or it might be quicker depending on how you do it. So that, yeah, this did come up last year, but that doesn't mean it wouldn't come up again. And often, they'll give you a similar question, so this kind of making salts thing, but with a new context. So I saw a question recently where it said a student did it with calcium, chloride, and sulfuric acid, and they were trying to make a specific salt, but those were the wrong things to use to make that salt. So you had to correct the substances that were used to make that salt, in order to get the full mark. So to make sure, as I said before, that you use all the information in the question and you apply your knowledge to whatever new situations you have in front of you. So both metal oxides and metal hydroxides react to make salt and water. And then acids react with metal carbonates to make salt and water and carbon dioxide. Okay, so remember that carbon dioxide is made because of the carbonate, right? But otherwise, you have salt and water, just like with the others. And the salt, again, the name of the salt will come from the metal and from the non-hydrogen part of the acid. So, for example, if this was sulfuric acid, H2SO4, reacting with calcium carbonate, CaCO3, then the salt would be calcium, because that's the metal, and sulfate, because that's the non-hydrogen part of the acid. So the salt will be CaSO4, okay, plus water and carbon dioxide. And normally with carbonates, you should find that that balances automatically, but you may need more acid depending on which acid you have. So the making soluble salt practical is for everyone, but also relating to acids. If you're on triple, you may be expected to do the titration practical as well, and you'll also have the related titration calculations. So we've done quite a bit on calculations recently, but I'm going to go on to that now. Remember, the main formulae are moles equals mass over RFM, and obviously RFM comes from the relative atomic mass of your substance. Now this is taken from the AQA periodic table, so if you're on Edexcel, this will be the opposite, as in the relative atomic mass will be at the bottom. Make sure for the relative formula mass or relative atomic mass, you always take the larger number. Hydrogen in this example is the same, the atomic number and the relative atomic mass is the same, but for every other element, the relative atomic mass is larger, and that's because the relative atomic mass is protons plus neutrons. Okay, so I'm not going to go over that, but just make sure you also are able to find out how many protons and neutrons there are in any element based on the periodic table. How long are you planning to do this live for? I'm just going to go through as much as I've planned, which is calculations. Okay, so it's going to be over relatively soon. I normally do them for about half an hour, but today, because it's the day before the exam, I will also be planning to go through a past paper later. Probably not live, but I will be putting it up on YouTube and possibly IGTV, so keep an eye out for that. I know that Science with Hazel has just done an AQA one, so I may do an Edexcel one just to make sure I'm not doing the same thing, and to make sure as many people can be helped as possible, because obviously Science with Hazel is also great and she's got her AQA video out now. So I'm probably going to go through the Edexcel paper from last year later on today. Okay, so just going back to calculations. So this is the main equation, moles equals mass divided by RFM, and obviously you may be expected to rearrange that in lots of different ways. So if you want to find the mass of something, then you need moles times RFM. And if you want to find the relative formula mass of something, then you need RFM equals mass divided by moles. Okay, so make sure that you can rearrange equations. because that's an important skill, and that's one of those mathsy skills that you're expected to know. I will stay a bit longer if people have specific questions, but for now I'm just going to go through what I've planned to do. And if you do have specific questions, I will be happy to answer them. I can stay a little bit longer. I know that today people are a bit stressed, so feel free to ask questions as you go along. Okay, so the second one, and this one is mainly for triple, because as I said, it relates to titration. Moles equals concentration times volume. For this, make sure this dm cubed is highlighted, because you need to make sure that your volume isn't dm cubed. They'll often ask you something about 250 centimeters cubed or 500 centimeters cubed. So you need to divide that by 1,000 to convert your centimeters cubed into decimeters cubed. So that's often the volume is given in centimeters cubed, so make sure that you do that conversion, okay? If you're not on triple, you don't need to use this calculation really at all, but you may be expected to find the concentration of something in grams per decimeter cubed, okay? And as you can see from the units of this, grams per decimeter cubed, grams divided by dm cubed, you calculate the concentration by looking at the mass divided by the volume. So how much mass was dissolved in a certain amount of volume. So it might ask you 4 grams of copper carbonate was dissolved in 500 centimeters cubed of water, and then you'd be asked what's the concentration in grams per decimeter cubed of that substance. So you take the 4 grams, divide it by the 500 centimeters cubed, which is 0.5 dm cubed, and that will give you your concentration in grams per decimeter cubed. So that's for double. Okay, but for triple, you may be expected to do it in moles per decimeter cubed. This third one here is the gas volumes equation. So moles equals volume divided by 24. And again, this is in decimeters cubed, okay? So it's divided by 24 if the volume is in decimeters cubed, or you could do volume divided by 24,000 if it's in centimeters cubed. But basically, you have to make sure that the units match. If you're an AQA and you're doing energy, you may also be expected to do the calculation for energy change equals bonds broken minus bonds formed, because bonds broken is breaking bonds is endothermic and making bonds is exothermic, okay? And so this is going to be an increase in energy, and this is going to be a decrease in energy. So that's why you've got bonds broken minus bonds formed, because you have the same amount of energy released by a bond when a bond is made than is absorbed when a bond is broken. So in a reaction, the overall energy change is the total energy that's taken in by bonds being broken minus the total energy that's released when bonds are being formed. And a key thing about exothermic and endothermic reactions, as well as this calculation, is you may be expected to explain why a reaction is exothermic or endothermic based on its bond breaking and bond making. And for that, you need to say, basically, the 3 main points for that are making bonds is exothermic, breaking bonds is endothermic, and then the final thing is the decision. So if more bonds are broken, or if more energy is released when bonds are broken than is absorbed when bonds are made, if more energy is released when bonds are made than is absorbed when bonds are broken, then that's going to be an exothermic reaction. So basically, deciding on whether something is an exothermic or endothermic reaction, or explaining why, is all to do with the balance between how much energy is released when the new bonds are made in the products versus how much energy is absorbed when the bonds are broken in the reactants. Just seeing some questions. GCSE biology has some really weird questions, like discuss why scientists came to this conclusion. Do you think something like that could come up for chemistry? Yeah, it's possible. When you say discuss why a scientist came to this conclusion, it's often to do with using evidence and previous knowledge put together. So you might have an existing theory, and then new evidence comes to light, and then that affects it. I haven't seen the biology questions, so I can't really talk much more about that. But how do you know which calculation to do, because there's so many stages? Well, often the exam will actually step it out for you and make it slightly easier for you. It's only in the much harder triple questions where they might not give you the breakdown for those questions. I'm having a look at this. Do you say that in the calculation, or is it in a separate question? So I'm not really sure what that was talking about now. I probably missed what you actually said. Okay. Finally, required practical. So I mentioned already the soluble salts one and the titration one, but you've also got, you need to be able to know how to separate mixtures of different types. So the main ones are filtration, distillation, crystallization. You may need to know a bit of chromatography, even though generally chromatography is in paper 2, and fractional distillation, which is used to separate liquids that have different boiling points. For some of the boards, the required practical is electrolysis of an aqueous solution, and for that you'd be expected to describe the apparatus used and also explain what is made at the positive and the negative electrode. Relating to this, I know that a lot of people want to know about half equations, and a lot of people are always confused about that. And that reminds me of something I haven't mentioned yet, which is redox. Okay, so redox came up earlier briefly when we were talking about reactions of acids, because often those are redox reactions, but also to do with ionic bonding and ionic with ionic bonding, where the metals lose electrons and the non-metals gain electrons. So any time that electrons are gained or lost, it's a redox reaction, because redox stands for reduction and oxidation. Okay, and some of you may remember oil rig. I've written it backwards, so I'm going to write it like that. So oil rig means oxidation is loss of electrons and reduction is gain of electrons. Okay, so if you're on foundation tier, you don't need to know about it in terms of electrons, you just need to know about it in terms of oxygen. So oxidation is the gain of oxygen and reduction is the loss of oxygen. But it's the other way around for electrons, that's why you have oil rig. So oxidation is the loss of electrons, reduction is the gain of electrons. So in electrolysis, if you have, let's say, copper sulfate solution, this is a common one that might come up. So we've got aqueous. That means that you have also hydrogen ions and hydroxide ions in that solution. So you need to make a decision about which one's going to be formed at each electrode. You always have the least reactive positive ion being formed at the negative electrode. So in this case, it's going to be the copper, because copper is less reactive than hydrogen. So your copper 2+ gains 2 electrons to become the copper element. Okay, and you may be expected to write state symbols in here as well. You don't need a state symbol for the electrons, but you do normally have to write the negative sign on it. And then copper would normally be formed as a solid. Okay, so the half equation shows the ion gaining electrons to make the element, and this is gaining electrons, and so therefore it is reduction. Okay, and the other electrode, at the positive electrode, we're going to have not the sulfate, but the hydroxide. Oh, I've just realized I made a mistake and put that positive, it should be negative. So the hydroxide gets formed at the positive electrode if you have a sulfate or nitrate or carbonate. So the only time that hydroxide is not formed in an electrode is if you have a halogen. So if you have sodium chloride or lead bromide or something iodide, then the halogen is going to be formed. But if there's no halogen, then the hydroxide will be formed. And the hydroxide makes oxygen and water. Okay, and then it releases electrons, and then this has to be balanced. And because we have because we have 1 oxygen in the water, we actually have to make that 2 and this 4, and therefore 4 electrons. So if you aren't seeing, obviously, if you're on Instagram, you're not seeing my screen, then go onto YouTube and you can see exactly what I was writing. So 4 hydroxide ions go to oxygen plus 2 waters plus 4 electrons. So with half equations for electrolysis, make sure that at the negative electrode you have a positive ion gaining electrons, and that means it's being reduced. And at the positive electrode you have a negative ion losing electrons, and so therefore that is being oxidized. Okay. So I think I've gone through pretty much everything that I was planning to go through, and we've gone a little bit already beyond the half an hour that I normally do, but like I said, I am happy to stay on a bit longer if you guys have any specific questions. I'm just having a look through. I think I've missed some of your comments. So could you go through bond energy calculations? Okay, I'll have a look at that. There's a past paper question that I have that we can go through. Do you know if there's any resources for practice questions? I've done all the past papers and specimen. apart from the boards where you get all the past papers and specimen, I think that Save My Exams and Physics and Maths Tutor are probably the places to go for past papers, but they're probably all from the boards as well. So really what you're doing is getting questions from other boards that may not be as relevant to you, but as long as you're working with specification, you know what you need to know, then that's fine as well. What's the difference between simple and fractional distillation? So simple distillation is normally when you have a dissolved solid in a solution, so dissolved in, let's say, water. And so you evaporate the solvent, so the water, and then it condenses. So you separate out the solvent, which is in this case the water, leaving behind the solid that was dissolved in it. Fractional distillation is when you take two or more liquids that have different boiling points. And so as you heat the mixture, you control the temperature to control what the boiling point is, and you just gradually increase it, and you'll have one of the liquids distilling off before the other liquid, or if you have more liquids, then you'll have several stages where they'll keep evaporating at higher and higher temperatures, and you'll be able to separate them off based on their boiling points. Just having a look through some of the questions. Okay, I think I missed a few things, but yeah, so if you missed the very beginning, I did give some key pieces of advice for approaching your exam questions. So if you missed the beginning, then go back to the recording later on. Someone just said, can you do percentage yield? I've already got bond energy in my head, so I'll do bond energy and then percentage yields. Okay, so I can go through some questions, but it's going to be way more helpful for you guys if you are on the YouTube live stream, because you'll be able to see my screen, and it'll be really hard for me to do both at the same time. So there's past paper question on bond energies that I went over recently. Let's have a look. So this is just flicking through the AQA past paper from last year. I'm pretty sure I saw a bond energy calculation here. So hopefully you guys have already had a look through this. It's always a good idea to have a look through past papers, because it gives you an idea of the style of question that you're going for. Okay, so and kind of highlight the key words that come up in it. Here we go. Here's a bond energy question. Okay, so bromine reacts with methane in sunlight. Figure 9 shows the displayed formula for the reaction of bromine with methane, and it shows you all of the formula, which shows you every single bond in bromine and methane and what's formed. So table 3 shows the bond energies and the overall energy change in the reaction. Okay, so we've got bond energies in table 3. We've got figure 9 showing each of the bonds. Okay, and that's really important information. Calculate bond energy X for the CBr bond. Okay, so bond energy X, so there's a missing bond energy in the table, and we need to work out what that is. Okay, so as I said earlier, the total energy equals the bonds broken minus the bonds formed, or at least the energy in each of them. So the first step is to work out how many bonds you have that are breaking and how many that are being made. So from methane, we have 4 CH bonds. So we do 4 times 412, because that's the CH bond. Okay, and then we have 1 Br-Br bond. So that's 1 times 193, because that's the amount of energy that's absorbed when bromine breaks, minus the bonds formed. So 1, 2, 3 times the CH bond, 412, 1 times the CBr bond, which is X, because we don't know it, that's what we're trying to find out, and then 1 times the HBr bond, which is 366. Okay, so the overall energy change is also given to us, which is 51. Okay, so if we plug everything into our calculator, we should have everything except for X. Oh, remember the sign, I almost missed it, minus 51. Okay, I don't have my calculator to hand, hang on. Okay, so basically minus 51 should equal the total of the bonds broken minus the bonds formed. If you want to rearrange it first to make X the subject, that's absolutely fine. So X will go on the left-hand side and minus 51 will come onto the right-hand side. So that will actually become a plus 51. So that means X will equals 4 times 412 plus 193. And then minus 3 times 412, minus 366, and then plus 51. So the answer should be, I haven't checked with the mark scheme, but the answer should be 290 kilojoules per mole. So basically what I did was I took 51 and I moved it to this side, and I took X and I moved it to this side. So X equals 4 times 412 plus 1 times 193 minus 3 times 412 minus 366 plus 51, because it's minus and minus. So that's what I did, and I got 290. I might have made a calculator error, but that's how you do the bond energy calculations. Okay, I'm just having to look. It wasn't on last year. What would you do for tomorrow? Both. Okay, cool. What are polymers? As far as I know, polymers is not on paper 1, but polymers are when you have alkenes and they get added together to form long chains of repeating units called monomers. Percentage yield. I don't think there's a percentage yield calculation in this question. Here we go. So percentage yield is basically the amount of substance that you make in terms of mass. So the yield is how much is made in terms of mass as a percentage of what you should have made from the theoretical yield. Okay, so the calculation for percentage yield is actual mass over theoretical mass times by 100. So it's just a percentage of how much you actually made over the amount that you should have made based on your moles equation. And that's the thing that people often forget, is that the theoretical mass you normally need to calculate from the moles equation that you're given. Okay, so for a stage 2 reaction, which is up here, you've got given information about stage 2, 40 kilograms of titanium chloride was added to 20 kilograms of sodium, and you've got the equation as well. The theoretical maximum mass of titanium produced was 13.5. So in this case, they give you the theoretical mass, you don't work it out, but normally you might be expected to work it out. Okay. If the yield was 92.3%, calculate the actual mass. So this is actually a rearrangement of this calculation. They've given us the yield, which is 92.3. We have the theoretical mass, which is 13.5, but we don't have the actual mass. Okay, so we need to rearrange this equation by doing 92.3 times by 13.5 and then divided by 100, and that should give us the actual mass. Again, I should have brought my calculator. So 92.3 times by 13.5 divided by 100. 12.46 is what I got, 12.46. Okay, so 12.46. What I said earlier about checking your answers, this is where this is really important, okay? 12.46 kilograms and 13.5 kilograms are quite close to each other, okay? So that to me is positive reassurance that I've probably got the right answer. We would expect that the actual mass will be a little bit less than the theoretical mass, and that's what we have. We've got a little bit less than 13.5 for our actual mass, and that's often because something goes wrong in the reaction. Maybe some stuff is left behind, not everything reacts. It might be a reversible reaction, in which case sometimes the product will have reacted back to make the reactant. So there's various reasons why we might not get 100% yield, but you would expect, and so a mental check you should do when you do a calculation is that you get a number that's similar to the theoretical mass you're given. So if you had got 1,246, you'd have done most of it right, but you needed to divide it by 100. And that mental check would help you to realize that you might have got the wrong answer. for those of you who are on here, this might be an interesting question to have a look at as well. So it's about limiting reactants, which is another thing that some people were asking about a lot last week. So we get given the mass of titanium chloride and the mass of the sodium. So we have the mass of these two things. And we had to explain why the titanium chloride is the limiting reactant. So you need to show your working to show that you're going to have not enough moles of the titanium chloride to fully react with the moles of sodium. Okay, so we've got given the relative atomic masses, so we do moles of titanium chloride equals 40 divided by the relative formula mass, so that's 48 plus 35.5 times 4. Okay, I'll do that on the calculator. So 40 divided by 48 plus 35.5 times 4. I get 0.21. Okay, then you work out the moles of sodium. Okay, so that's 23 divided, sorry, not 23, 20 divided by, that's the mass, divided by 23, which is the atomic mass, and I get 20 divided by 23, 0.86, 0.869. Okay, you also need to consider that this is a 1:4 ratio. Okay, so we need to have 4 times as many moles of sodium as titanium. Okay, so 0.21 times 4, 0.21 times 4 equals 0.84. And that shows that we don't have enough moles. So this is 0.84 is less than 0.86. And that shows that the titanium chloride was the limiting reactant because we didn't have enough to fully react with the sodium. Another way you could have done the same exact question is to use the 4 of the sodium in the relative atomic mass. You could have done 4 times 23, and this would have given you 20 divided by 4 times 23, and that would have given you 0.434. Actually, I think it should have been more like, anyway, but the idea, I think I need to check my answer. 20 divided by, let's see, 23 times 4 is 3. I think my calculator's gone funny. 23 times 4 equals 92. So 20 divided by 92 equals 0.217. Yeah. So if you did it with a 4 times 23, you'd have got 0.217, which again, 0.21 is less than 0.217. So that's the same kind of idea where hopefully you guys are still following along. So basically, for showing why something is a limiting reactant with both masses, you calculate how many moles you have of each of those by doing mass over RFM. And you either use the moles ratio to work it out, or you use the number of moles in the RFM to show that as a ratio, you don't have enough moles of the limiting reactant to fully react with the other reactant, which is therefore in excess. Okay, so let's see. I think I might have missed some things. Okay. Have any of you guys got any more questions? Those of you guys who are on here. Naming polymers. Okay. Percentage abundance for isotopes. Okay, so this is normally to do with calculating relative atomic mass. This is for Abby Hines. I'm not sure if you're still on here or not. Let me actually, I think I can check. Abby studies. It seems like it might be the same person, but I don't think it is. Okay, so someone asked about percentage abundance for isotopes. That's to do with calculating relative atomic mass, where you take the sum of the isotopic mass times by the relative abundance, and then you add it for all the different isotopes you have and take an average. So limiting factor, will one of them always be limiting, or could the ratio be equal? It's possible that the ratio could be equal, but it's very, very unlikely, because unless you've measured really, 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 really accurately, there's almost always going to be something left over. So theoretically, obviously, you can have equal masses and stuff, but in reality, when you actually do reactions, you normally have a little bit of one left over. So you would normally find there is at least one limiting reactant. I also went through half equations earlier, so if you missed that, then you can go back to the replay, and I did go through half equations. If you're on the YouTube, I'll be able to show you that briefly as well, if I can find the right thing. Oh, here. Yeah. So if you're on the YouTube, I'm showing you now all the things we went through. We're going through it very briefly. And we did half equations where we were talking about the required practicals of electrolysis. And we did copper sulfate solution being formed, and we did the half equations for that. So just remember the rules for how you decide which is formed at each of the electrodes. Okay, so... Okay, cool, guys. Well, I think I've gone through pretty much all of the stuff that might come up in paper 1. Earth structure and tectonic plates is not on the chemistry paper 1, as far as I know, for any of the boards, unless you're on a really weird board. So I won't be going over that today. But yeah, I think I've gone through pretty much all the stuff that is possibly going to come up. Make sure you know your required practicals, but please do not regurgitate them in the exam, okay? Sometimes the question will ask you in the context of some new information. So make sure you can apply what you know to some new information, okay? Can you... Naming polymers is on paper 1. Okay, so naming polymers is just taking poly and putting in brackets the monomer. So let's say the monomer is ethene, then the polymer made from ethene is poly brackets ethene. If the monomer is propene, then it's poly, P-O-L-Y, brackets propene. Yeah, that's all it is to making polymers. I think actually you're right, there's not too much about polymerization, but it also comes up in covalent bonding for one of the boards, where you're expected to be able to know that polymers have covalent bonding that holds the monomers together, and that they are a long chain. But that's really all you have to know for paper 1. Paper 2 is where it asks in much more detail about polymers, so we'll go through that after paper 1 is finished. Okay, so yeah, thank you guys very much for joining the live. I hope I went through as much of your questions, as many of your questions as possible, and as you probably had, hopefully. As I said, I've got the exam tips back on the screen now on the YouTube live, which is on my link in bio. So if you want to have a look, I said read the whole question, use all the information, answer every single part of the question. Even if you don't know, make sure you take a guess. And be specific. Don't use the words it, they, or amount. Be as specific as possible, especially for something like writing your observations. Say, for example, the solid turned black and the solution turned blue, rather than it turned black. That won't give you the mark. Check your answers, especially for calculations and equations, and keep an eye on the time. You normally have about a minute per mark, with about 5 minutes of leeway, which is for checking or for a little bit extra time you might take on your longer answer questions. So, please don't put down more than one answer, especially if it's a multiple choice or a tick box, because that means you can't get given any credit. Please don't regurgitate your notes without reference to the question. Always refer to the question. Don't repeat the question. It's a waste of time. You don't get any credit for saying a question like, explain why this is covalent bonding, and then you just say this is covalent bonding because. Often that's an even more, often people repeat even more than that, which is a bit of a waste of time, especially if you only have 1 minute per mark. So make sure it's as specific as possible, and don't repeat the question. Okay, guys, so that's it for me for now. I will be, right after this, I'm going to be going through the Edexcel Chemistry Paper 1 and putting that online, because as I said, Science with Hazel has done it for AQA. So all of you guys who are AQA, go and watch Science with Hazel's walkthrough. I will also do it later on for paper 2, and I will do Edexcel now. So some of you who are on Edexcel will be able to see that and go through that past paper. So thank you guys very much for joining. Really best of luck for the exam tomorrow. Please let me know how it goes, and I'll see you again soon. Okay, bye. Save. And YouTube, let's see what's going on here. Stop.